Welcome to the Pathfinder's Codex, where we try fun things in computer programming, for both beginners and seasoned coders. Today we're going to cover the basics of 2D shaders in the Godot game engine. This is part 1 of a 4-part learning series, with each video walking you through several 2D practice shaders. We'll go through and pick apart each one to see what makes them tick. Now, these videos will only contain the simplest of shaders, and hopefully I've organized them in a way so that each practice shader helps you build a foundation for later videos. The original versions of these shaders can be found on GodotShaders.com. All credit for that original code goes to those creators and those that inspired them. However, I've simplified and compacted a bunch of the code to make it easier to learn from, so what you see today probably won't match up with the code that's on the website. Okay, let's get to it. First, let's look at the type of shader we're going to be using. We'll be working with Godot's CanvasItem Material shaders that affect 2D textures and sprites in our projects. There are other types of shaders too, but we'll only focus on these 2D materials for this series. A CanvasItem Material shader allows us to change an image or a texture on the screen using math and other cool techniques, pixel by pixel. At its core, it allows us to change any of the pixels in the original image or texture, and we can use any number of ways to determine how and what pixels to change. For most of these practice shaders, we'll use the Godot logo icon as the sprite texture. We'll sometimes use a second image, a pixel art mech suit, so we can play around with border detection and other neat effects like transparency. Let's see where they show up in the Godot editor. A shader is assigned to textures, canvases, and sprites within your game using a material resource. You'll usually find the material properties in the Canvas Items section in the inspector. Each material will need a shader script. That's where the instructions for the shader will live, and they'll have a .gd shader extension over here in the editor file system. We could also create materials or scripts once and reuse them on many different nodes. But for all of the shader examples we're covering today, each one will have its own material and a unique script file. Once the material resource and the script is attached to the node, we can open it and start writing the shader code. The code will appear in the shader editor down here. And since these shaders run in the editor, we won't need to restart the game to see the effects. Pretty cool, huh? If you find these practice shaders useful, be sure to subscribe and leave a comment to let me know you want more of this type of content. Alright, let's jump into our first shader. This one's called ColorChannelRed, and as the name suggests, it's all about changing the red color channel of an input texture. It's a good place to start because it introduces us to the most basic elements of shader programming. The fragment coordinate and UV system, how to access the source texture, how to manipulate the output colors, and using uniform variables to control different input parameters into the shader. Here's how the code works. The shader type canvas item line tells Godot that this shader will be used on 2D textures or sprites. All of our practice shaders will use this mode. Then we define a uniform variable called red. Uniforms are handy because they let us set parameters directly in the Godot editor, or through scripts, without changing the shader code itself. It's great because we can see them over here in the inspector, change the values here, and then see the results in real time in our scene. In this case, the red variable controls how much red is included in the texture, with the default value of 1. We can change it down to 0 and we instantly see the effect on our logo. Shaders later in this series will have a bunch of input parameters here, with all sorts of controls and purposes. Next, we have the fragment function. This is an important built-in function that runs for each pixel of the texture, allowing us to modify the image's appearance. For the first line, we grab the color of the logo using the texture function, and make it the default output color for this fragment. Now, there's a lot packed into that one line, so let's take a look at it step by step. First off, the special texture variable. This built-in variable is the actual image or texture that the shader is working on. It could be a sprite's image, a tile map texture, or pretty much anything we've applied the shader to. Think of it as the raw source that we're about to read from. In this first shader, it's the Godot logo image. Then there's the built-in UV variable. This is how we figure out which color of the texture we're looking at for the current pixel. Remember we said that this fragment function runs for each pixel? Well, our fragment function doesn't actually know anything about pixels. It only knows how to use a fragment coordinate to tell us which color it's working on, which is conveniently stored in the UV variable. Throughout these videos, I might refer to them as pixels, but that's not exactly accurate. They're fragments, and the UV is the color information for the current fragment we're working on. You can think of UV and fragment coordinates as kind of a grid map of the texture. They start at 0, 0 in the top left of the texture and go all the way to 1, 1 in the bottom right corner. The y-axis can sometimes be flipped depending on the engine you're using, so be aware of that if you ever see your results turned upside down. These coordinates are normalized, which means they're based on a percentage of the texture rather than the actual pixel dimensions. So whether your texture is 100 pixels wide or 1,000 pixels wide, the UV will always work the same way and will always go from 0 to 1 on both axes. Now, when we combine these two variables with the texture function, what we're doing is sampling the pixel from the logo at the current fragment UV coordinates and reading that color. This gives us the pixel's original color, which will be a vector4 variable. That's just a fancy way of saying that it's made up of 4 individual parts. R for red, G for green, B for blue, and A for alpha, which is the transparency. We'll use vector4 for many colors, but sometimes we'll ignore the alpha transparency and just use a vector3 instead. These vector formats are commonly referred to as the RGB color format, and they're used all over in video, graphics, and shaders. So the last thing the code does is assign that vector4 RGB color to this color variable. This is another special built-in variable in a fragment function. It's where we'll set the output color for the current fragment, and it's how we'll change the final image. Whatever value we assign into this color variable is what the fragment will show on the screen. Now that we've got the original pixel color and made it our default output color for the pixel, we can start making changes to it. Here's the cool part. You can change each of the color channels individually in a vector4. So in this shader, we're only messing with the red output channel, which is color.r. But you could do this with any of the channels like color.g or color.b. We take the input from our red uniform and put that directly into color.r. The other parts of the color, like green and blue, won't be changed, and they'll look just like the original image. This means that instead of the red intensity from the original texture, we're replacing it with whatever value we sent in as the red uniform. If the red uniform is set to 1, then the red channel is fully saturated. It'll be at max intensity. If it's set to 0, then the red channel will be completely turned off. And if it's somewhere in between like 0.5, it will get a softer red. This range, where a variable only goes from 0 to 1, is common in math and shaders, and we call it a normalized or continuous value. We'll look at mapping values using interpolation and normalization in later shaders. So in just a couple of lines, this shader gives us complete control over the red channel of our texture, while leaving the green, blue, and alpha channels completely untouched. It's super simple, and it's a perfect starting point to see how shaders let you manipulate textures on a pixel-by-pixel basis. Still with me? Alright, now that we've got the basics with our first shader, let's move on to something a little bit more advanced, but still beginner-friendly. This one's called ReplaceColor, and it's all about swapping out one color in your texture for another, using some creative tricks. In this second shader, we'll use the mech suit texture instead of the Godot logo. This shader introduces a couple of new concepts, but don't worry, we'll break it all down step by step. Here's how it works. First, we start with the same line as before. This tells Godot we're working with a 2D texture or sprite. No surprises there. But this time we'll have 3 uniforms that we can control for inputs. It has the color to be replaced, a threshold to control how close a color needs to be for it to be replaced, and the color to replace it with, which we'll call the mask. Like before, we see these parameters in the Godot editor when viewing the material. But unlike before, 2 of these parameters are not just basic numbers. The color to be replaced and the mask color are vector3s. Notice in the editor the 3 parts show up as X, Y, and Z, but we'll treat those as R, G, and B channels to represent a color. Colors in Godot are stored using 0 to 255 for each channel, instead of the normalized values between 0 and 1. We'll see in a moment why that's important and how we're going to deal with it. Before we check out the fragment function, I wanted to mention something else about these shader uniforms. Not only can we change these parameters in the editor to see the effects in real time, but we can also use these variables in our code and scripts. Here's how it would work with the first 2 shaders in our series. Here we can set the red channel we saw in our first shader directly in code. And in the ReplaceColor shader we're talking about now, we can set both the mask or color to be replaced in the same way, using Godot's color constants. This makes things simpler to read and allows us to create one shader to do a lot of different things, even animate and tween the values. Okay, back to the shader code and our fragment function. In the first shader, we saw how this function runs for all pixels in the texture, and it used the UV color details for each pixel. We'll do the same here. First thing we'll do is make the default output color the same as the input color from our mech sprite. But here's where we're going to change it up. This shader has two decisions to make. First, how does it know if it should replace the current color with the mask? And second, what color does it actually use for that mask if a color needs to be replaced? Let's answer those in reverse. In our first shader, we saw how to change just the red channel of the vector4 color variable. This time we're going to change 3 channels at once, red, green, and blue channels. Assuming we want to replace the color, this line of code takes our color stored in the mask uniform, normalizes it, and sets the result as our output color. The mask variable stores a color channel using values between 0 and 255, because that's the standard way colors are represented in Godot's color class. But in shaders, we typically work with values between 0 and 1. So to convert the mask color into a format we can use, we divide each of its red, green, and blue components by 255. This normalization scales each of the values so that they'll be in a range between 0 and 1, making them compatible with our shader calculations. Notice that we're only changing the RGB channels here. The alpha channel, which controls transparency, remains untouched. This means if the original texture had a transparent area, it'll still be transparent after the color swap. Vector math can be complicated, and while we'll see a lot of it in the shaders throughout this series, we won't be covering the theory in detail. Instead, we'll focus on practical applications like this one, where simple division helps us work with colors in a way that makes sense for shaders. Now let's go back to the first question. How does the shader decide if it should leave the original color from the input texture, or if it should use the mask color? What this if condition is looking for is the distance between our current fragment color and the color to be replaced, and if that distance is within our threshold. Earlier we used color.r to access just the red channel, a single number between 0 and 1. Here, color.rgb represents the entire color as a vector3 containing red, green, and blue components together. To decide to replace a color, we need to compare two colors. Color.rgb is the current color of the fragment taken directly from the input texture. Since shaders expect colors to be between 0 and 1, we also divide this vector variable by 255, just like we did with the mask color earlier. This ensures that both colors are in the same 0 to 1 range before we compare them. This conversion process is something you'll see often when working with colors and shaders, especially when dealing with values that come from external sources like Godot's color class. Once we have the two normalized colors, both ranging from 0 to 1 in each channel, we'll pass them into the distance function. This function measures the distance between two colors, but what does distance mean here? Simply put, it's the straight line measurement between 2 points in either a 2D or a 3D space. Think of it as drawing a ruler between any 2 points in a square or a cube. And since these colors are 3-part vectors, and they're normalized between 0 and 1, they can be represented as a 3D cube. This allows us to use the distance function to say how close are these two colors inside the cube. So now we know how far apart our original fragment color is from the color that we want to replace. We compare that distance to our threshold uniform. The threshold is how short the ruler needs to be to trigger the color swap. If the distance is smaller than this value, we trigger the color swap. A low threshold makes the condition stricter, meaning colors must be very similar, while a higher value here allows us for greater variation with more colors being replaced by the mask. If we only want to replace an exact color, we would set the threshold to 0. Like before, you can play around and change these shader parameters to instantly see the effects while you're in the editor. We'll take that a step further in the next shader by using uniform hints. And like we talked about earlier, you can even change uniform settings using code to animate or interpolate these inputs over time, or in response to different events in your game. Okay, let's keep going with shader number 3. Now let's bump it up a little and use the HSV color model. We'll control the hue and saturation of a color instead of using RGB colors. We'll create a rainbow type effect in our image and call it a RadialHue shader. This shader will have one uniform, called Influence, that lets us control how much of the new color is blended into the original texture. This influence represents the amount of color blending to use, and it ranges from 0, or having no effect, to 1, having full effect. This is the first time that we're seeing a hint range for a uniform. The hint range here makes it really user-friendly by allowing us to adjust the parameters in the Godot editor using a slider control. There are other great hint features that you can check out to make it even more useful, and we'll see some of those in future shaders. Now let's talk about the first of the two functions in the shader, the HSV to RGB function. This function will convert an input color from an HSV value to its corresponding RGB value. But why do we need to do this? Well, HSV is super handy when you want to work with colors in a way that feels more natural, like you might see in a color wheel or in a rainbow. Chances are you've seen this format in color pickers in many different tools and applications. Instead of thinking about how much red, green, or blue a color has, the HSV lets us think of colors in a more natural way. The color itself is called the hue, and we'll represent it as an angle on a color wheel. In this shader, we normalize the hue to a value between 0 and 1, where both 0 and 1 represent the same hue and all available colors are spread across that space between 0 and 1. The saturation is how vivid the color will be, with 1 being fully saturated and 0 being white or completely unsaturated. And the value is how bright or dark the color is, where 1 is the brightest and 0 is completely black. Using HSV allows us to better control gradients and moving around within the color space, and not have to worry about exactly how much red or green or blue goes into whatever color we're working with. But then computer displays really don't understand HSV. They use RGB when they show pixels, so this function will help us convert any HSV color we have into their matching RGB color. In later shaders, we're going to see the reverse of this function, where it converts the RGB format back into an HSV, but we won't need that for today. Okay, let's shift gears and look at the fragment function, where we'll use the HSV conversion to change our fragment output colors. The first step is to adjust our coordinate system. This is important because our RadialHue effect is all about the relationship between our current pixel and the center of the image. Luckily, the data in the UV variable wraps around itself, essentially repeating the data in all directions. So by subtracting our current UV value from vector 2.5, we'll always be comparing our current pixel to the center of the texture instead of the top left corner. Once we have this adjusted position, we can figure out the hue by using the arctan function, which gives us an angle of the current pixel relative to that center pixel. That angle becomes our hue value, which smoothly wraps around the texture to create a continuous spectrum of repeating colors. Next, we'll calculate the saturation by taking the length of our position vector and multiplying it by 3 to make it more pronounced. In simple terms, the further away a pixel is from the center, the more saturated the color will become. And we'll leave the value component fixed at 1, ensuring that our colors stay bright and vibrant, but we can just as easily change this value if we wanted to. Finally, we pass the 3 parts, the H, the S, and the V, into our HSV conversion function, which gives us back the RGB color that our shader can use. We then blend this new color with the original fragment color from the texture by multiplying it by our influence uniform. Think of influence as a dial that controls how much of the new effect will be added to the original image. A value of 0 means no change, while 1 means 100% application. The actual blending here is simply done by adding our new dynamic color on top of the existing texture color, using the += assignment notation. We could do this with a simple equals assignment, but then we'd lose the original image color and only see the RadialHue introduced by our shader. And that's the breakdown. With this shader, we're taking advantage of some clever math to map each pixel's position into a beautiful rainbow-like overlay. The closer a pixel is to the center, the less vivid its color shift, and the further out, the stronger the effect. We can control the amount of color merging using our influence uniform, either in the editor or even in code, to make some interesting animations or sequences. It's a great example of how shaders can combine with math, color theory, and creativity to produce something visually appealing. In future videos, we'll continue to build on these ideas, exploring even more creative ways to manipulate color and lighting for our 2D shaders. Well, I hope these first 3 shaders were useful. We covered some of the most basic concepts, like the fragment function, the color and UV variables, and the HSV color space, with each idea helping us better understand what shaders do and how they work. Knowing how these components fit together and being able to play around with them yourself, you'll be better prepared for the more complex shaders in the upcoming parts of the series. Be sure to subscribe so you get the next video where we're going to go over the next 4 practice shaders, including introducing vertex manipulations and adding timing features to our toolkit. Thanks for watching the Pathfinder's Codex, and never stop learning.